Hey everyone, it's Joel, Andrew, and Lizelle here, and today we will be learning section 2.6, Rational Functions and Asymptotes. Hey everyone, thank you again for joining Joel, Andrew, and I today for lesson 2.6, Rational Functions and Asymptotes. Throughout the video, we will be going over some vocabulary terms and helpful examples. So take out a pen or pencil and a notebook as we head right into this lesson. Okay, so the first thing we're going to cover is our vocabulary terms. We'll be covering vertical asymptotes as well as horizontal asymptotes. To start off, let's discuss vertical asymptotes. To locate a vertical asymptote, set the denominator equal to 0 and solve after the expression has been simplified. Any factors that cancel out when the expression is simplified creates a hole in the graph at those values. The next vocab term you want to know are horizontal asymptotes. To determine where a horizontal asymptote occurs, compare the degree of the numerator to the degree of the denominator. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is the line y equals 0. If the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is the line y equals the lead coefficient of the numerator over the lead coefficient of the denominator. If the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. Knowing that we covered all of the vocab terms, let's head into the first example. So in this example, we will be identifying the domain, the holes, all of the asymptotes, and all of the intercepts of this function. The function we will be working on is f of x equals 2x plus 1 over x squared minus 4. So the first thing we're going to do is identify the domain. The domain is always determined by the original function. So while looking at this function, do we have the possibility of a domain restriction? Yes, due to the fact that we have the factor x squared minus 4 in the denominator. We know that causes a possible restriction because any value of x makes that denominator 0, which makes that function undefined. So how do we find the restriction? In order to do that, we take the denominator and set it equal to 0, and we solve. Once we set it equal to 0, we get x squared equals 4. There we take the square root, and we find that x cannot be 2, and x cannot be negative 2. Therefore, our domain is from negative infinity to negative 2, union, negative 2, 2, union, and to infinity. Next, let's go ahead and find our holes. First thing you want to do is simplify the function. As you can see, our numerator is already in its simplest form, so we can leave that alone. But our denominator can be simplified and factored out. When we factor it out, we end up getting x minus 2, x plus 2. There you could look ahead and see nothing will cancel out here as far as factors go. So whenever we have no factors that cancel out, that guarantees that your graph will have no holes. Next, we'll look and find all of our asymptotes. First, our vertical asymptotes. If we go back and refer to our vocab, we can conclude that in order to locate a vertical asymptote, we set the denominator equal to 0 and solve after the expression has been simplified. Earlier, while we were finding the domain, we took our denominator and set it equal to 0. We also did that when we were simplifying the equation when finding our holes. When we did that, we found that x equals plus or minus 2. Therefore, our vertical asymptote would have to be x plus or minus 2. For our horizontal asymptote, we have to look at our degrees. The degree of the numerator is 1, and the degree of the denominator is 2. Again, if you look back and refer to the vocab, it says that if the numerator is less than the degree of our denominator, our horizontal asymptote will be at the line y equals 0. So the horizontal asymptote of this expression is y equals 0. Lastly, we'll be finding all of our intercepts. Let's start off with our x-intercepts. To find the x-intercept in our function, we have to plug in 0 for y in order to find x. So when we do that, we get 0 equals 2x plus 1 over x squared minus 4. Carefully, we want to solve this because this is usually the case where we find an irrational function. To begin solving this for x, we have to solve by getting rid of the fraction. So I'm going to solve this by multiplying x squared minus 4 to each side. There, x squared minus 4 cancels each other out. And notice what happens since we're plugging in 0 for y. When we multiply x squared minus 4 by 0, we get 0 and end up with 0 equals the numerator 2x plus 1. Now we solve this equation for x. First, subtract 1 onto both sides, and when we do that, it leaves us with negative 1 equals 2x. We want to divide both sides by 2, and since 2 cancels out, we end up having x equals 1/2. X equals negative 1/2, sorry, which makes our x-intercept at that ordered pair of negative 1/2, 0. For our y-intercept, we plug in 0 for x. When we plug in 0 for x here up top, I'm left with 1, and then on the bottom, I'm left with negative 4. So our ordered pair is 0, negative 1/4.
Example 2. Finding a hole in the graph. Let's say we have the equation x squared times 2x minus 4 divided by 2x minus 4. To find a hole in the graph, we must find what makes the numerator and the denominator 0. 2x minus 4 is the denominator, so we must set it equal to 0. We add 4 to both sides, and then divide both sides by 2. We then have x equals 2. Therefore, x equals 2 makes the denominator 0. We then replace the x's in the numerator with 2. We then find the numerator to be 4 times 0, or 0. The numerator and the denominator are both 0 when x equals 2. We have found the hole in the graph. We graph the equation like normal. We find the equation to be x squared when x is not equal to 2, as the 2x minus 4 cancels out. After you have finished graphing, place an open circle at x equals 2 on the graph you had just made.
So now that we are done with example 2, let's dive right into example 3. We're pretty much going to do the same thing we did in example 1, where we determined the domain, holes, all of the asymptotes, but this time we will be graphing this function. So our function for example 3 is f of x equals x squared minus 1 over x squared minus 2x minus 3. So just like last time, let's begin with finding our domain. So if you look ahead, you can see that the denominator of our function does not have a domain restriction. Therefore, our domain is all real numbers, and if we were to write it out, it would be negative infinity to infinity. Next, we'll focus on finding our holes. So the first thing you want to do is factor the numerator and the denominator. And when we factor our numerator, we end up with x plus 1, x minus 1, and x minus 3, x plus 1 in the denominator. If you were to compare the two, you'll notice that x plus 1 shows up both in the numerator and the denominator. Because those factors match, it tells us that we are going to have a hole. We want to set our factor to 0. When we solve for x, we get x equals negative 1, but beware that x equals negative 1 is not the whole. It's only one of the coordinates. So to get the other, we're going to take x equals -1 and plug it into our reduced function. Now that I know x plus 1 matches, we can cross those out of our function. So that means my parentheses will be -1, -1 over -1, -3. Simplify the equation, then reduce it, and we end up with our whole, which is -1, 1/2. Moving on to our asymptotes. First, our vertical asymptote. Again, we want to focus on the denominator just like we did last time, but the key is that you do not include any factors that canceled out. The only piece of the denominator I want to be concerned about is that x minus 3. To find the asymptote, we want to equal x minus 3 to 0. In this case, when we do that, our vertical asymptote would equal x equals 3. Next, we'll head right into our horizontal asymptote. To determine our horizontal asymptote, we have to look at our degrees. If you look at the top and bottom of our original function, you'll notice that the degree of the numerator and denominator are both x squared. So if you look back at the vocabulary we had in our notes, you'll see that if the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is the line y equals the leading coefficient of the numerator over the leading coefficient of the denominator, which in other words, the horizontal asymptote would equal 1. Now that we have that done, let's see if we can graph all of the asymptotes we found. Starting with my vertical asymptote, x equals 3. When we do this, you want to remember that when drawn, it is a dotted line. Moving on with our horizontal asymptote, we'll be drawing that at y equals 1. Next, we need to draw a hole which is at -1, 1/2. So to represent that, draw an open circle at those values. As you can see, our asymptotes have cut our plane into 4 different possible locations. For this function to land, I think the hole might give us a big hint as to where it lands. But if all else fails, make yourself an XY table and plug in some values. Our asymptote is +3, so we can't use +3. So how about we use 2 for the left side and 4 for the right side? Plug them into the table, and it's fine to plug them into your reduced function, so the one with those matching factors have been crossed out. Plug them in and see if you get the same thing I do. So when I plug in for 2, I got a y value of -1. When I plugged in 4, I got a y value of 3. So these ones are actually plottable and fit nicely on my graph. And if nothing else, they tell you where this graph lands. So 2, -1 is a point, and 4, +3 is a point. So we know in general it's going to hug the asymptotes. It's going to be real close to that hole, but you want to be sure you don't fill it in. And this quarter hugs the asymptote like that. And there you have example number 3.